Welcome to the annual Marden lecture. Thank you all for finding your way all the way over here to Dubai. In 1992, before most UW students were born, I was in high school and my mother bought me this book. It's called Chaos, Making a New Science. She wanted to encourage my burgeoning love of mathematics, and she was an elementary school teacher, so she bought me this book. This book explains, and to my mind praises, the discoveries of several pioneers in what would become my research area: Steve Smale, Edward Lorenz, and James Yorke. In fact, these are among the first to recognize that chaos is a scientific and mathematical phenomenon that can be studied and understood in many settings. Dr. Yorke and his co-author, T.Y. Lee, gave the science of chaos its name in a 1975 paper entitled Period 3 Implies Chaos. Over the past few decades, these ideas on chaos have come to play a major role in our understanding of everyday phenomena, such as the maddeningly unpredictable weather and multiple biological, chemical, and physical processes that surround us every day. Professor Yorke is a distinguished university research professor of mathematics and physics at the University of Maryland's Institute for Physical Sciences and Technology, and has been at the University of Maryland since 1963. How's that for loyalty? First as a grad student, and then as a professor after earning his PhD in 1966, the same year as local trivia thoughts. Alan, Steve, the first PhD was awarded at UW-M in the Department of Mathematics. More on that later.
Okay.
It was 66, right? Yeah.
How many PhDs have you awarded?
2. The first one was so good we closed up shop after that. Dr. Yorke believes that a degree in mathematics is a license to investigate the universe, and has devoted much of his professional life as an educator and researcher to sharing these ideas broadly with countless students and young researchers across many fields of study, and helping others to learn with his infectious enthusiasm for knowledge. In fact, to my delight, I got to meet Professor Yorke for the first time in 1996 on a prospective graduate student visit to the University of Maryland, and I've gotten to know him a bit over the subsequent years, enough to assure you we're all very lucky to have him with us today. Now, who do we have to thank for this?
Marden.
Morris and Miriam Marden. Every spring we get to invite a distinguished lecturer to Milwaukee to give a public math lecture. This Marden lecture is named for Professor Morris Marden, who founded the PhD program in mathematics at UW-M in the 60s in a time when there were no PhD programs on this campus. We are grateful to receive continuing support from the Miriam and Morris Marden Fund, which has made this lecture possible for the last 30 years, as well as the cookies that we'll have after the talk in EMS 495. Just follow the crowd. I'd like to give a shout out to the Morris and Miriam Marden's son and his wife who are here today. Philip and Sherry, would you please stand up? Okay, without further ado, it is my great honor to introduce Professor Yorke, who will tell us about the many facets of chaos.
Well, I'm delighted to be here to tell you about chaos. I should warn you that everybody already knows about chaos. In fact, I tend to say that the last people to find out about chaos were the mathematicians and scientists. And if you look back in the 70s and often much later, all of the examples of dynamical behavior are basically non-chaotic. And anytime you can write down equations and solve the equations explicitly, you're guaranteed to have no chaos as a differential equation, because it means you have to have enough regularity that there's no chaos. I once visited Wisconsin. I was talking to a young lady, and I asked how her parents met. And she says, well, her mother took a taxi one time, and hit it off with the taxi driver, and they wound up getting married, and this young lady was the result. And so, had the mother taken, if I can call her the mother, the pre-mother took a different taxi, this young lady wouldn't exist. And that's the way life is. Or imagine, if you want to make it more directly personal, just imagine when you were conceived, if slight change, you wound up the opposite sex. How would that change your life? It's kind of a little random event. So, another lady told me she couldn't come to my lecture because she had 2 kids at home, and she had the plumbers working on the bathrooms, and there were no toilets. And I said, well, she already understood chaos. So there are a lot of different ways of thinking about chaos, and I think we're pretty much talking about the same kind of things. What we're talking about are systems which are deterministic. So we're not talking about random stuff as the stock market is kind of random. It's too complicated. But imagine you have a system where it's got laws for how things behave. It's predictable in the short run, but not in the long run. That little events set things off. There's a 2,500-year-old concept of the blind men and the elephant, where there are several blind men. The number depends on the telling. This is a Buddhist parable where, so what do we have here? This fellow encounters the elephant's ear, and well, what's an elephant? It's like a big fan, one of these big fans. And another one encounters this tusk, and he says it's like a spear. And no, this one in back, it says a rope. And all of these, chaos can be somewhat similar if you don't understand all the aspects of chaos. And the way to think about chaos is actually, I'm going to give you some examples. One might ask, if you're dealing with dynamical processes where things evolve in time, you've got steady state behavior, an example being this table. And I predict that this table will be in the same spot when my lecture ends. That's pretty steady. Another one would be periodic behavior or quasi-periodic behavior. Let me show you here. So this is a pendulum hanging from a pendulum axis. So here you have it's pretty much of a periodic motion going back and forth. And another example, more complicated, would be the moon. And the moon fits into, it's actually got 3 periods. And the 3 periods correspond, well, one is 27 or so days where it goes around the Earth in that period of time, but it's also got a period of 8 years, roughly, and another one of 18.6. And so if you look in the sky, as people in ancient times regularly did, and you would see the line through which the planets move, the plane of the ecliptic. And the moon would stay close to the plane of the ecliptic, but it would be one side or the other, and occasionally crossing the line of the ecliptic. And they try to keep track of all of these crossings. And the crossings occur every so many years. And they basically had a quasi-periodic system with 3 periods, and they were able to determine all 3 periods. And it's not clear how they did that. But for a while, see, it would oscillate. Here's the plane ecliptic, and the moon would be oscillating back and forth. And then sometimes it'd be oscillating by bigger amounts, and sometimes by smaller amounts. And all of these things they kept track of this with detailed records. I'm not sure how they did. They didn't have very good observational techniques, and they didn't have periods. Sometimes it would be moving through the sky faster because it was closer to the Earth. So the moon varies in distance from the Earth from 220 million miles, 220,000 miles to 252,000 miles. And it's a complicated motion. And this happens to be some pictures I took from New York. And we had, this was called a supermoon, where the moon was unusually close to the Earth. See, as the moon goes around the Earth, the plane is tilted. And so it can be going up behind the Earth, not in line with the sun. It's tilted out of the way, and so you don't get an eclipse. So you only get 2 eclipses a year. And this is a particular kind of complicated motion. Now, again, the reason I'm talking about that is I'm saying that basically in nature, you tend to get 3 kinds of behaviors, which are steady state, periodic, and I'm counting the quasi-periodic of the moon, and chaotic. So what is chaotic? So here's a very simple example where you imagine you have you think of it as having a circle, and so you've got a 0 point, and you take some initial angle, which is x, and you double the angle. And then you double that angle again, and then you double the angle again, and you just keep on going. So if we think in terms of revolutions, if you start off 0.33 of a revolution away, and you start iterating it, that goes to 0.66, and then 1.32. Well, that's 0.32. You don't count the entire revolutions. And it keeps on going. Now, imagine instead of starting with 0.33, we actually start with a third. Well, 0.33 versus a third doesn't seem like much of a difference. But 1/3 goes to 2/3, which goes to 1/3, and it's period 2. And what's happening here is that the difference between these two is 1/300. Now, if I take 2 different angles and I double them both, the difference will be twice as big. And so the difference between these first 2, does that show up? No. The difference between these 2 is 1 in 300, and then the next time it's 2 in 300. Now it's not 3 in 300, it's 4 in 300. And it just gets blown out of sight very quickly. And I started off with 2-digit precision, or 1 in 300, whatever that is, 3-digit. And if I'd started with 10 digits, it would only take a little bit longer for the same phenomenon to occur. And what's happening is that these effects are doubling with time. And the physicist might say, well, that's not a very mathematical thing. It's not real. It's not. But in fact, it abstracts out the reality of many physical processes. And the reason chaos was discovered big time in the 1970s was because of the availability of small computers where people could explore. Before 1975, computers were good at refining your knowledge. If you wanted to build a dam and you wanted to figure exactly how it should go, it could help you build this very complicated dam. But it was not a good exploratory tool until we could get our hands on them. So here we're talking about an aspect of chaos, which is the exponential the exponential divergence of trajectories. When you're talking about the weather, a weather model will have a doubling time in the air. So if you have a weather model, you've got an estimate of the weather all over the world. And there will be some errors involved. And those errors will double in time, typically, with a certain amount of doubling time. And it might be 2 days. And so after 2 days, you've got twice as much of an error as you did. Your observations aren't very good to begin with. And it's a whole world model. And how do you figure out what the weather is doing over the Pacific Ocean? It's not easy. So I want to point out that here's something sort of attributed to Benjamin Franklin, and it's also attributed to other people hundreds of years earlier. And it talks about for the want of a nail, the shoe is lost. He's talking about a battle and a horseshoe and a rider of a horse. And the nail is lost, which means the shoe is lost. And the shoe is lost, and then the horse is lost because the horse has lost a shoe. Now you might say, well, if you lose a horseshoe nail, it's pretty unlikely you're going to, if you lose a nail, it's unlikely you're going to lose the shoe. And if you lose a shoe, it's unlikely you're going to lose the horse. But these are quite likely, I mean, they're quite possible events. And so we can see a cascading of slightly less likely events. And if this fellow was on the horse was carrying a critical message, indeed, you could wind up with the kingdom being lost. He says that the army is about here, the enemy is around the bend. And so Benjamin Franklin made his money by writing an almanac, as most of his money. And this is one of the things he published. He had to keep coming up with things to fill up his almanac. And he didn't do it with reports on lightning and electricity, but so he did a lot of things. And so here is two examples. Here we have a quadratic map, and this quadratic map would be a quadratic like so, or a tent map. These are two examples of continuous maps on an interval. And the idea is you take a particular value of x, you evaluate it, you get f of x, take that as the new x, whatever that is, you apply it again, and you keep iterating this example, just as we did with the example on the circle, where we kept doubling that. And Lee and I wrote a paper, Period 3 Implies Chaos, that Suzanne mentioned. And basically, it said that suppose on that line, your first x is here, and then the next x is bigger, and the next x is bigger, but then the next one is even lower than what you started with. Or it comes back. That could be a period 3 point. Big, bigger, back to where you start, that's period 3. And if your continuous map has a period 3 trajectory, we're talking about simple maps on an interval, then there are periodic orbits for all periods. So for example, you pick a number like 17, there will be some starting point. If you start exactly at that starting point, then after 17 iterations of the process and not before, you will come back to where you started. For the same map, and pick another number, 117. There'll be another initial point, which gets you back, which is as period 117. All of these coexisting in the same dynamical system. And all of them coexisting in this totally simple dynamical system. I think it's fair to say that this dynamical system is pretty much too simple to illustrate anything accurately. But it gives you the flavor that the reason our lives are complicated is not because our lives are so not just because our lives are so, have so many different aspects to them. Even when you have a single aspect, namely a single coordinate, a single variable, you can get very complicated, non-repetitive behaviors. So this is what we had in mind. There was also, we also said that there's another behavior. There are two aspects of this theorem. And the other is that you can take two initial points and you can follow them. And as you follow them forward, occasionally they'll get as close as you want and then move apart and keep on iterating them pairwise, and they get getting even closer and they go apart. And there's an uncountable set of such points, any two of which have this scrambled behavior. All within the same continuous map, only assuming that you have this period 3 behavior. So this has been a very popular thing for students to look at. We actually did not name chaos we did not give a definition of chaos in our paper, even though this paper is taken as the beginning of the idea of period 3 implies chaos, is the beginning of it, chaos as a mathematical term. But see, even back then, I felt that there is no single definition, because here we have two kinds of behaviors, infinitely many coexisting periodic behaviors. Boom, let's call that chaos. Or here we have this, okay, what this represents, I call this a scrambled behavior. I'm thinking of eggs, where you're scrambling eggs. This is very difficult to describe when you convert it into other languages. But you just imagine two atoms in the eggs, and assuming it doesn't get hard, you just keep on scrambling it, and they'll get arbitrarily close and move apart, and close together and move on. In the scramble, the whole thing behaves like that constantly. A totally different kind of behavior from this behavior. Now, some people might be interested particularly in this behavior, and some people might be interested in this behavior. So if I give this definition to somebody who's interested in this, they can't do anything with the definition. Got the idea? And if somebody is dealing with plumbers, they don't care about either of these definitions. So the idea is that depending on how you come at chaos, and certainly this is a single example, but you're coming in from different ways and you have different kinds of, different aspects of the chaos. This is the elephant. Maybe this is often true of real things. An example of chaos being actually applied, Halley's Comet came by, what was it, 1984? 85? But there was another comet that was coming by even earlier. And that was the Jacobini-Zinner comet. And the Europeans were going to send a spacecraft to Halley's Comet. And so the Americans said, let's send a spacecraft to the Jacobini-Zinner comet. Now here's the problem. There was no money for a spacecraft. Hey, don't stop, don't give up. We had a spacecraft in orbit, and this picture shows you this. So this is if you have the Earth, moon about 250,000 miles, 1 million miles out in the direction of the sun is 93 million miles. 1 million miles out, there's a balancing point, Lagrange point, and we basically had a satellite in orbit, orbiting this make-believe point of the Lagrange point. And so if they put it at the Lagrange point, then the sun's radiation of all kinds of wavelengths would drive out would wipe out any radio signals from this. So they have to have it offset. And you could have a periodic orbit that's just offset. And they said, let's send that one. And so there's a group, Robert Farquhar, at the Hopkins Applied Physics Lab who figured out a way to do it. And the idea is they had 200 pounds of fuel on board. Now, usually, they have these rocket launches, these immense rocket launches with millions of pounds of fuel, I don't know how much. So here they had 200 pounds of fuel. And so they could only give it a nudge. But when you have chaos, giving something a nudge is good enough sometimes. And if it's a particularly unstable environment, you may have a lot of choices as to which way it'll go from the time you give it a nudge. Now that elephant, you give them a nudge, maybe you can't tell which way it's going to go. But with the solar system, we basically know the rules. Now I'm not saying the moon is chaotic, but it's a source of chaos for a third particle, which is the spacecraft. And so they gave it a little nudge, which is 10-mile-an-hour nudge. And that's my bicycle speed. See, I could have told Elon Musk, hey, why don't you start with rockets that are already out in space? Makes everything a lot easier. Okay, so now this picture I'm showing you is in rotating coordinates. So you imagine you're above the solar system looking down, and as the Earth rotates around the sun, you rotate your camera so that you get this picture. So the dynamics looks a bit peculiar with the rotating coordinates. And here's the moon, and this is a near pass of the moon. Now when you go behind the moon pulls you forward and accelerates you and gives you extra angular momentum both. And so then basically it gives you a kick. And so you get a large amplitude oscillation. And so it's using the moon as a repetitive creator of chaos. No, my mistake. Here was the first one. It goes in front of the moon, and since it goes in front of the moon, it's being pulled backwards, it loses energy. And so the next oscillation, whoops, what happened? Why did that? Oh, this is simply telling you it's preserving kinetic energy plus potential energy minus angular momentum is a constant in the right coordinates. So here's what happens. This is one near pass of the moon. It comes out here, and the timing is just such that it's got another near pass of the moon, but it's behind the moon and gets kicked out again. And then it comes in for a third near pass of the moon, and it slows it down, and it goes a fourth near pass of the moon, and it kicks it out again. And then finally it comes to the fifth near pass of the moon. All of this figured out in advance. And this time it again goes behind it, so it's got a double bounce, and it kicks it out into space. And it goes off 60 million miles. It's 60 million miles from the Earth when it goes through the tail of the comet. Okay. So now the reason this was possible is not because of the fantastic precision. You could say, look, you're telling me about chaos, and yet you're saying they could figure this out, all these repetitive bounces. That's impossible. Well, the trick is that they did have this 200 pounds of fuel, and they kept on applying the rocket fuel with multiple burns and correcting for the fuel, despite not having any optics on board showing where they were. And as a result, they could control the chaos to do whatever they want. So later, my most cited paper is titled Controlling Chaos, 1991. But we didn't do this work. This is Robert Farquhar's fantastic work. And so now I'd like to talk to you about a different kind of aspect where the chaos can be hidden. And I'd like to talk about a simpler kind, mathematically simpler kind of chaos is where you've just got a pendulum, and but you have a motor, a clock-like motor going back and forth, driving the pivot point. And so sometimes it's driving it with the pendulum swing, and it gains energy. Sometimes it's against it, and you're losing energy. And so you've got this periodic clock-like thing, and you wind up with rather complicated behavior. And you can do this in such a way that there are different steady states of the pendulum, where the pendulum can be rocking back and forth, kind of lopsided, or it can be rocking back and forth on the other side, lopsided, or it can be swinging overhead. And all of these behaviors are stable in the sense that if you start near that state, you actually get pulled into that state. Hey, I thought this was a lecture on chaos. Yes, there is hidden chaos. So the basin of attraction of one of these states would be the set of initial conditions. So you can, the initial conditions for this single pendulum is you have an initial angular velocity and you have an initial position. So for example, you start off here with angular velocity 0 and you let it swing, and it'll get caught eventually in one of those three, and almost certainly it'll get caught in one of those three kinds of periodic behaviors. And we say it's in a particular basin, depending on which of the three it goes into. And so you can color code three different sets of initial conditions. So you take a grid of initial positions, 1,000 initial conditions, and 1,000 initial velocities, and you've got a grid of 1,000 by 1,000, and each one of these you can color code according to where it's going to go. So this is the equations of a force damped pendulum. And so here is a picture that one winds up with. Again, so we're taking 1,000 by 1,000 set of initial points at time 0, and we're letting them go and run, and these all go to the green attractor. And I guess the green attractor, I think, is the one which is going overhead. And the blue and the red, they're different attractors. So in this, there would be one point where if you started in the green with that particular velocity, you'd return there after one cycle of this machine, this periodic twisting of the. So this you can think of as a map, and you see a very complicated picture. And this complicated picture is showing you a very complicated pattern. These are predictions. So you want to understand predictions of something really complicated. Let's start with something simple. Here you want to predict. If you're over here in the blue, it's pretty easy to predict what's going to happen. You're going to go to the blue attractor. But if you're near the boundary, and up here you can see there's a lot of stuff that looks like it's near the boundary between these regions, then it becomes very difficult to predict. So we would say this is an analytic map, nothing complicated about it. I'm going to give you two copies of this picture next to each other. And the idea is that here you're taking the initial angle of the pendulum, anywhere from 0 to 1 or 2 pi, whatever you call it. And then 2 pi is the same as 0, so when you put these pictures together, it's actually on a cylinder. And you get this very complicated behavior.
So is the green connected? Like, is that entire green region connected?
Yes. And I can give you a proof. Okay, and here's the proof. So here we have a point. And what's going to happen is that if you take a point here and a point here, they're both going to wind up here, right? After some period of time. It might take 100 cycles of this clock, or it might take 1,000, but they'll both wind up close together. Okay? And you can draw a line between the 2 points after time 100. Therefore, they're connected. Now, that seems like a weird proof. I've just left out a line. How short a proof can you give? Just don't give any details. Well, what happens, though, is if you go backwards in time from any point on this line, you stay in the green. Because the green stuff is, if you go forwards, it's going to go in here. So basically, that line will wind up over here, but be extremely contorted. It won't remain in the picture, but it'll start off wherever we said here, and it'll eventually come winding through the green over here. So that'll be a connected curve which connects these 2 points. Does that sound plausible? Good. I convinced one person. So here's another, same kind of thing, but we have a zoom where, now if you zoom in on the green, you just get all green. If you zoom in on any one of these colors, actually, here the green and the yellow are basically the same behavior. I won't tell you the details there, but imagine the yellow and the green are the same. And as you zoom in on a boundary point, you keep seeing all 3 colors. And anywhere on the boundary, you zoom in on the boundary, and everywhere you're going to see all 3 colors. So try you again, same thing. And you just keep seeing all. So we call this the Wada property. In topology, there were things called Wada, basins of Wada, which was a pun on a Japanese mathematician named Wada from Kyoto. No, sorry. They were lakes of Wada in Hawking and Young. And so we called them basins of Wada. But basically, what happens here is that they have these weird boundaries. Now we have, here's a slightly different choice of parameters. Instead of having 3 of these attracting points, there are 8. We're rather surprised to find that. So the idea here is that here, between these 2 colors, there's a smooth boundary. So let's identify, just as I was saying, identify the yellow and the green, let's identify the purple and the white, okay? So there the boundary is not complicated, but everywhere else the boundary is complicated. And you can ask, how can you draw? So here is an example in the plane where I take 3 regions. Let's go back to 3 for the moment. And 3 connected regions, which basically fill up the plane. And there's 1 point. These are unbounded areas. I can give you another very simple proof of that, but I won't. So these are these area, all of these are unbounded in the plane. And there's only 1 point here where all 3 meet. And I ask you, can you find an example in the plane of 3 connected regions where there's 2 points on the boundary of these 3 regions? You get the question? And the answer is, despite our lack of imagination due to looking at the geometry of Euclidean geometry, this has the property that every point is on the boundary. It's on the boundary of all 7. So if I take any point on the boundary and I draw a little circle around it, no matter how small, it'll contain all 7 colors. And this is for an analytic differential equation. And so basically, Wada and Brouwer and the topologists of the early 1900s were investigating these ideas, but their examples were so weird that they weren't dynamical systems, they were just geometric configurations that they seemed just totally unlikely to ever occur. And yet here, we look at a pendulum. It's not that we love pendulums, it's that pendulums are something that's hard to argue with. That here it's just a pendulum, and the whole you got this Wada property. And why do we get this? Hey, this is electron chaos. Because there's chaos on the boundary. The behavior on the boundary is chaotic. I want to show you this picture again. Again, the way we do this is the color coding. So you could imagine looking at this pendulum, and you could actually look at it dynamically, and you look at it stroboscopically. So you've got, it's being periodically forced in every period of the rotor, of the pivot. Every periodic, you flash the light and you get to see it where it is. That's a stroboscopic view of this thing. And so you start off with stuff that's very close somewhere to the boundary, and you start looking at it, and you see where these points go. And here is this new yellow set is basically a chaotic set, or where it crosses the boundary is a chaotic set. Now, once it's in the green, of course, it's going to go to the green. When it's in the blue, it's going to go to the blue. But you can look at it probabilistically. Suppose I knew that this gentleman was going to get hit by a car tomorrow. I say, okay, now probabilistically, where is he going to be today? Okay? I have no idea, but that being hit by the car has nothing to do with where he is today. And this is the kind of behavior here. So this is the conditional probability that if it hasn't already been hit by the car, being pulled into one of these basins, if it hasn't already been hit by the car, it can be anywhere on this yellow. But if it's in here, it's going to get hit by the car and get pulled in to the basin. So that's where the chaos is. This is another aspect of chaos. And chaos occurs in ways in which you wouldn't expect. So we also dealt with a chaotic system. Eugenia Kalnay and Ed Ott and Tim Sauer and this whole group of guys dealt with a weather forecasting problem of how do you update a weather model. And so we dealt with what you might call a baby dynamical system for the weather people. It has 3 million variables specifying the location of specifying the weather on the entire Earth. So that was the state. So the state would be, you've got 500,000 actual points in space, and you know the average wind velocity, the vorticity, the ozone, the temperature, the humidity, all these variables at each of these points. And the question is, how do you update it tomorrow with the new data you've given? And we worked on this, and these are basically chaotic models. And we based it on the idea that it isn't really all that chaotic. So this is called data assimilation. And so this is an example where you start off with an estimate of the jet stream, and you see where it is after 4.5 days. And this turns out to be that it's doing a pretty good job. So you got different predictions as to where the weather model will be, where the jet stream will be, depending on exactly how you started up. But they're pretty much in agreement. And this loop meant that there was going to be a storm in this area, and they predicted a winter storm. And they actually got a winter storm. That's after 4.5 days, predicting that this would look like this. Whereas sometimes after 2.5 days, you can't predict. So why do they predict 7 days ahead? The reason they predict 7 days ahead is because if they predict 6 days ahead and the other channel predicts 7, then everybody will watch the 7-day channel. Let's see. I'm going to move on and say some more about this double pendulum. See, what chaos is about is predictability or the lack of predictability. And so this has the steady state behavior. You see the table is still there. I was right. And it's got periodic behavior. And in the textbooks, you would see that in the 1920s, they would talk about the double pendulum, the equations, they knew the equations. This is where the two pendulums are going in opposite directions, and then they can also go in the same direction, roughly periodic, and the time of oscillation is actually different. But if you were in the 1920s, you would try to keep the students away so they couldn't do this. And now, what is that? Is that periodic or is that steady state? Now, of course, this has some friction in it, and so the friction, I like to show them and show how it decays. But you see, it's not very predictable. And we had one where it had no friction, so we had to throw it out. So I'm going to ask you, is there anybody who isn't here? Good. So you're all involved in this game except the guy with the camera. Do you often get mentioned in the lectures?
Only when I fall down.
Okay. Okay, so this will eventually run out, and the blue one will stop going through the silver one. See, we make it sound more valuable by calling it silver instead of aluminum. But okay, it'll stop going through, and the idea is that you're supposed to predict faster than anybody else in this audience. You're supposed to be the #1 predictor. And if you get this, we will hire you to predict the weather, and people will throw eggs at you. But, so what's going to happen is, you're going to tell me, you could either email me, if you think it'll no longer go, but that doesn't go very fast. So here's a better way of doing it. Here, you clap like that. You think, hey, that's your statement. Your statement saying, I think the blue one will no longer go through the silver one. Boom! That's my prediction. Speed of sound. Okay? And if you're wrong, you get a second try. Nobody would clap if they thought they only had one chance. You only get 2 tries, okay? So Suzanne, if you would accompany me, we've got to help try to pick out who wins this event. Whoever wins gets to shake hands with Suzanne. Okay. So you got the name of the game? You got to understand? Okay. You want to be first. That doesn't mean you wait until everybody has already clapped a lot. Although, you still get one more try. So we're all about predictability. See, if you started off almost twice in almost exactly the same situation, the pattern of oscillations will be rather different. In fact, sometimes it'll It seems to be dying. Okay, so who won? Who, in your opinion, won? She's going to, what? Somebody who?
Who over there? Yeah.
Where?
That way. Or no, who?
They won't claim credit. Okay, we're going to do it again. It's everybody against him. Because after somebody had to win, right? Even if everybody will deny it. Okay, so let's go again. See if you can do it again. Now, the idea is, now you've seen the pattern, can you do a better job at predicting? And I got to say, I'm not very good at it, and even though I've had this pendulum for years, because it doesn't always end the same way. Sometimes it'll end up swinging back and forth with lots of energy. So you see, it's telling a different story. Okay, so what you've seen is chaos in action. Now again, this is not quite chaos because it does run out of energy and chaos keeps on going, but it's much more like that example I showed of the pendulums where it's the where will it be if it hasn't actually settled down. So this runs out of energy, and it's another aspect of chaos which is hard to attribute. Which chaos, how would you define chaos of the examples I've shown that would include this? So we wrote a paper which was aspects of chaos, Evelyn, Sandra, and I, just talking about why we didn't define chaos. Because you can't define it. And if you've got a numerical computer and you're going to see certain things, you need a definition which allows you to describe what you're going to see. And if you're a topologist, the periodic orbits are great. And it goes on and on. So, it goes on and on, but I will quit. So that's it.
Spare a few minutes for questions?
Yes.
So what made you originally decide to look at period 3 as a kind of indicator of that?
Well, there is a history. Edward Lorenz, is there any markers in it? I don't.
Yeah, we'll have to do it.
Edward, I see it. Edward Lorenz came up with a differential equation. And I won't write the differential equations, but it's a three-dimensional system where it had this kind of an oscillatory behavior, somewhere around 1963. And he described the system, and it was basically a chaotic system. And he, so he got about one citation a year for about a dozen years. People really didn't recognize the importance. He did an extremely good job of describing his particular system, which he thought of as a baby model of the atmosphere, trying to describe the atmosphere. But the meteorologists felt, that's too babyish. That's not our atmosphere. And other people didn't know about it. So when our paper came out, we told people about this Lorenz model, and it really caught on. But here's another thing that he did in the paper. Is he said, okay, start off along here. Okay, look at that peak value. This is our z variable. And so this is z1. And now we follow it along here, and it comes up over here. This is z2. And you just keep on plotting. And so he plotted consecutive zn against zn plus 1. And so he gets a curve which looks like this. Very little thickness of the curve. And this is basically a dynamical system. You take a given value of z, call it zn, and you get out zn plus 1. It's a one-dimensional map. And so we had this chaos, but it reduced the system to this one. And this is what I wanted the paper to be about. Period 3 implies chaos. And so this would have the behavior that if you had an initial point here, and then your next point might be over here, and your next point might be over here, and then you get kicked over here to the left. It doesn't have to be periodic. It's just boom, boom, bust in the sense of economics. And that'll imply all that kind of behavior. So that's what we were trying to do, explain this, and say, hey, you can do it for any continuous map. It doesn't depend upon the structure of this, doesn't depend on where it came from. And that was the idea. And the reason we called it chaos is because we felt that this chaos is what everybody else means by chaos, within reason. So then people say, oh, but in the Bible, in the beginning, all was chaos. That's not how people use the term. That's the only use in the English language of chaos in that sense. Usually the chaos is bounded. Okay, so that's more than you asked. Anybody else?
Okay, if you're too shy here, come find Jim at refreshments after the talk at EMS E495. Let's.
So your assignment is to say, when you go home and you meet somebody, how are you going to tell them what is chaos? Did you get anything out of this lecture? Okay. Short-term predictability, but not long-term predictability. Okay? And tell them why we didn't define chaos. Thank you.